Hello, this is Professor Keen, and welcome back to my lectures on electricity, magnetism, and light at Wisconsin Lutheran College. We've been talking about the topic of conservation of energy. We've been reading the work of Herman von Helmholtz, his 1847 lecture called On the Conservation of Force. We're in chapter 11 of A Student's Guide Through the Great Physics Texts, and in this chapter, he is talking about the general concept of conservation of energy. In my last lecture, I talked about the old theory of heat. Now, this is relevant to the conservation of energy because the point that Helmholtz is going to be making is that the kinetic energy of motion can be transformed into heat. There's a conservation of energy going on there. So in order to understand that, one has to understand the old theory of heat, and that was the caloric theory of heat. The idea that heat is an invisible substance that can neither be created nor destroyed, and when it flows from one thing to another, according to this caloric theory of heat, when this heat fluid flows from one object to another, the object that it leaves drops in temperature, and the object that it enters goes up in temperature. So I was talking about that last time, and I was also explaining how a steam engine works. I think at the end of the last lecture, I mentioned that one of the architects of the modern science of thermodynamics, that is the study of heat, one of the architects, his name was Sadi Carnot, a French scientist, and he was an adherent of the caloric theory of heat. So it's interesting to note that many of the people, including Sadi Carnot, for example, who developed the science of thermodynamics, were fully committed to the caloric theory of heat. So let me say one other thing about Sadi Carnot, and then I want to talk about the mechanical or the modern theory of heat. So Sadi Carnot, he attempted to do measurements of how much heat can be, how much work can be generated by a certain amount of heat. So the question is, how much work can be generated by a given quantity of heat? So we all know, and this is what we talked about in the last lecture, we all know that when you have heat flowing from a boiler to a condenser, in the example of the steam engine that I gave last time, when you have heat flowing from a boiler to a condenser, that is from a high temperature to a low temperature, that flow of heat, if you organize it carefully, you can accomplish work by having the heat flowing from the boiler to the condenser pass into a gas that expands, driving a piston, for example. So this has many different engineering applications, most notably at this time the steam engine and the locomotive. So Sadi Carnot, being an engineer, wanted to know how much work can we get out of a certain quantity of heat. So if you have a boiler right here, like on a train, you're heating up water using coal, and you have heat flowing to a condenser or to some other cold object. In so doing, you can extract some work. And the question is, how much work can you extract? And he did a number of experiments to try to determine the answer to that question. And it's important to note that he fully believed that heat was a substance. Is a substance, according to Sadi Carnot. Okay, so he believed in the caloric theory. Now, here's the difficulty that arises from the caloric theory of heat that did not escape some of the scientists at the time. The difficulty is that it seems that heat can be generated by rubbing things together. You're probably familiar with this. If you take your hands and you rub them together, they get hot, right? So it seems like, from the perspective of caloric theory of heat, it seems like the substance of heat would have to be generated by motion, the motion of your hands. Now, the caloricists, how would they explain this? They weren't ignorant of this fact. So how did they explain this if they thought heat was a substance that could neither be created nor destroyed? Well, they appealed to the concept of latent heat. Somehow that heat must be stored in your hands in a hidden way. Kind of like the way heat is stored in water, and when it gets transformed into ice at 0 degrees Celsius, it does not change its temperature, at least while it's changing phase, and yet heat comes out of it. So there was some latent or hidden heat in the water that is manifested or shown eventually when it turns into ice, if you were to freeze it. So the caloricists might argue the same way. There is this hidden heat in your hand, and when you rub your hands together, that heat is made manifest or shows up. It comes out of your hands. Now, there's a scientist, Helmholtz talks about this, the scientist Sir Humphrey Davy, and I think Helmholtz talks about this on, I believe he talks about it on page 125 or 126. I don't remember exactly what this is, where this is, but he mentions that the scientist Sir Humphrey Davy, he rubbed together 2 ice cubes and caused them to melt. And the question is, if ice does not contain any latent heat. After all, the latent heat had been thought to be in water, and when you convert it into ice, then that latent heat is made manifest, it shows up. But if you already have 2 ice cubes, that latent heat isn't being stored in them at all, but if you rub them together, you can cause those 2 ice cubes to melt. So it seems like there's heat generated by motion in a way that seemed to be difficult to explain using the caloric theory of heat. So because of experiments like this and others that I'll be talking about in a moment, there arose a new theory of heat. So let's talk about the new theory of heat. The new theory of heat is called the mechanical, Helmholtz refers to it as the mechanical theory of heat, or sometimes the kinetic theory of heat. And what is this kinetic theory of heat? Well, the idea is, first of all, that heat is not a substance. Heat itself, according to this theory, is not a substance, as the caloricists thought. So, if it's not a substance, then what is this heat? Well, they said it is a form of molecular motion. Now, what does it mean that heat is a form of molecular motion? Well, it means that when you have a substance that to perception feels hot, it's not because there's some substance within it that's making it hot. Rather, the molecules that comprise that substance are in agitation. They're moving around, they're vibrating in such a way as to give us the perception that the object is hot. And what does it mean when an object is cold? Well, it means that the object has molecules that are in a lesser state of agitation. That is, they're still moving around, but less rapidly, and so we perceive that as being more cold. That's the idea. That's the fundamental difference between the kinetic theory of heat and the caloric theory of heat. So another way to think about this, maybe it would help for me to make a sketch. So what I'm going to do is I'm going to open up my sketchbook. And so you might think of a wheel. And this wheel, if it's spinning around, all the atoms that comprise this wheel are moving around in uniform motion. I suppose you might say just uniform rotation around. So I'm drawing here a bunch of the atoms that comprise this wheel. So this would be kind of an orderly motion of these atoms that make up the wheel. You could even describe this in terms of the kinetic energy of those individual atoms. The kinetic energy is an ordered form of kinetic energy because all those atoms are moving in a very predictable fashion around in a circle. Now, suppose that while these were moving around in a circle, we were to try to slow this down using a brake pad. So we have this clamp that's around this wheel that's able to squeeze the wheel. What happens when we squeeze the wheel? You know, this is how bicycle brakes work. This is how car brakes work. When we squeeze it, so this is before squeezing. And after we squeeze it, what happens is that the wheel is no longer rotating. These atoms are not spinning around this single axis in the middle anymore. Does that mean they've lost all of their kinetic energy? They've lost all of their speed? Well, no. According to the kinetic theory of heat, now those atoms, while not moving in an orderly way, now they're vibrating around within the wheel in a very disorderly fashion. So that's what I'm drawing. I'm representing schematically by these arrows. What this is meant to indicate is that while the entire wheel is no longer rotating around like it had been before, there's still a large amount of kinetic energy. However, it is disordered kinetic energy. So we might call this a state of ordered kinetic energy. And this is a state of disordered kinetic energy. And disordered kinetic energy is what we mean by heat. So sometimes they'll hear it said that the kinetic energy turns into heat when you apply the brake pad and slow this down. You could equally say this ordered kinetic energy turns into disordered kinetic energy, and heat is just a synonym for disordered kinetic energy. Again, the idea is that heat is not a separate kind of substance, an independent substance. Rather, it's a state of motion associated with randomness. That's the central feature of this new or kinetic theory of heat. So whereas this was at a low temperature and fast rotation, this would be at a high temperature, relatively high temperature, and no rotation. And maybe I'll say one other thing right now. It's not easy to reorder these random molecular motions. It's not like if you just waited long enough that these random molecular motions would suddenly all align with one another and this wheel would begin rotating once again. That's something that came to be known as the second law of thermodynamics, or it's associated with the second law of thermodynamics. Ordered motion tends to become disordered over time, but disordered motion does not tend to become ordered over time. There's kind of a preference in nature toward a state of disorder compared to a state of order. And that, again, is the second law of thermodynamics. This is something, if some of you take physical chemistry or thermodynamics, we go into in much more detail.